Today we're going to look at a pretty interesting differential equation. And that differential equation is y triple prime equals y prime times y double prime. So first, it's interesting to notice that this is a nonlinear differential equation. So let's recall that the linearity of a differential equation depends on linearity in the dependent variable and its derivatives. So of course there are no x's explicitly in this differential equation, and so we don't have to talk about linearity there. This is a so-called autonomous differential equation. But the fact that we've got a term y prime times y double prime is what makes this nonlinear, because that's quadratic in the dependent variable y and its derivatives, as it's the product of two of those objects. Okay, so anyway, let's dive into the solution. So we'll first notice that there are no y's here. We start with y prime. So we could indeed think about this as a second order differential equation in y prime. So perhaps that's the way to do it, but in order to maybe uncover the veil, we'll make a substitution. And so that kind of obvious substitution is to set, I'll call it z equal to y prime. But now if z is equal to y prime, then we get kind of these obvious equalities like z prime is equal to y double prime, and then z double prime is equal to y triple prime. So now we've got a new differential equation, which is, it's still nonlinear, but now it's second order. We have z double prime is equal to, well, now this is going to be z times z prime. Oh, but now looking at this, let's look at this right-hand side and observe we have a function times its derivative. So in my mind, that looks like we've applied the chain rule to some function of z. And in fact, if we multiply both sides by 2, we can see it more clearly. So here we'll have 2z double prime is equal to 2 times z prime. And now look at this. This 2 times z prime is exactly the derivative of z squared. So we have this is equal to the derivative with respect to x of z squared. Recall that z is a function of x, as I guess we'll point out explicitly up here that we're assuming that x is our base variable. So y is a function of x, and thus by extension z is a function of x. But then by the chain rule, well, this 2 is going to come down, and then we have to take the derivative of the outside function, which is z in this case. Okay, well, can we do something similar over here? Well, yes, we can. And that is, we can write this as the derivative with respect to x of 2 times z prime. Well, as the derivative of z prime is z double prime. But now look at what we've got here. We've got these two functions, 2 times z prime and z squared, have the same derivative. So the only way for two functions to have the same derivative is if they differ by at most a constant. So in other words, we have 2 times z prime must be equal to z squared, well, plus some constant, but I'm going to write it like this: plus minus a squared, where a is bigger than or equal to 0. So that way we can, well, that picks up all of the cases. Notice if we had done just plus a constant c, where c is any real number, well, if c is positive, then we can take its square root, and then we can write it like this. If c is negative, then we can take the square root of its negative and then write it like this. And then also if c is equal to 0, well, then this is essentially the same kind of thing here. Okay, so now we're going to look at each of these individually, maybe starting with the easiest case, which is this case when a is equal to 0. Okay, so why do I say that's the easiest case? Well, I think it's pretty clear that the differential equation is simplest then. Okay, so here we have 2 times z prime is equal to z squared. And now we're going to use the method of separation of variables. So I'm going to write that z prime as dz dx. So we have 2 dz dx is equal to z squared. And then we're going to move all of the z's to one side and all of the x's to one side. So this may seem kind of sketchy, but you can make this a little bit more careful if you want to. But that being said, the typical way to do it is like this, where we separate out the dz and the dx as we're about to. Okay, so anyway, that's going to give us 2 times dz over z squared equals dx. And now from there, we'll take the antiderivative of both sides, or the indefinite integral. So we have 2 and then the integral of dz over z squared equals the integral of dx. But now, each of those antiderivatives are fairly straightforward. So this left-hand side will give us, let's see, it'll be minus 2 times z to the minus 1, or minus 2 over z. And then on the right-hand side, well, that's going to give us x plus some constant. But that constant could be positive or negative, so we might as well make it x minus some constant. And now we can maybe multiply by a minus sign, and that's going to give us 2 by z is equal to b minus x. See, I did that just so I didn't have the hanging minus sign. But then we'll have z over 2 is equal to 1 over b minus x. And then finally, we have, let's see, it'll be z is equal to 2 over b minus x. Okay, but now while we're at it, let's maybe recall up here, we had z equal to y prime. So that gives us y prime is equal to 2 over b minus x. And then from there, we can just take an antiderivative, and then we'll have, well, what do we have? We'll have a function for y. Okay, so let's do that. So here we have y is equal to some constant c. I'm going to put that up front because when we take the antiderivative here, we're going to pick up a minus sign, and then it's going to be minus the natural log of, or I should say minus 2 times the natural log of b minus x. But now we might as well bring that 2 and that minus sign inside, and we'll have c plus the natural log of 1 over b minus x quantity squared. And then, well, maybe I guess I didn't really need to change the order here. And let's go up here and just collect what we have. So we have y in this case is equal to the natural log of 1 over b minus x squared plus some constant. And you might say, well, we started with a third order differential equation and now we only have 2 arbitrary constants, but we actually have 3 because this was a special case of our original constant being equal to 0. Okay, let's move on to the next case when a is positive. Now for our second case when a is positive. Now let's start over here again, and we're going to do our same separation of variables. So here we have 2 dz by dx is equal to z squared plus a squared. And I guess I shouldn't say a is positive here. Well, I should say that a is positive and we pick up a plus sign. So the next case will be a is positive and we pick up a minus sign. So let's maybe add that in here. So a is positive with plus, meaning this plus right here. Okay, so anyway, now let's get to solving this case. We're again, like I said, going to do separation of variables. So we have 2 and then the integral dz over z squared plus a squared equals the integral dx. Okay, so that's good. Now we'll take the antiderivative of both sides. And what is that going to leave us with? Well, there's kind of a well-known antiderivative for this left-hand side, so let's just recall what it is. So it'll be 2 over a, and then we have the arctan of z over a. And then for the right-hand side, what will we have? Well, we'll have x plus a new constant, which we'll call b. Okay, great. And then actually, instead of just taking a constant b here, I'm going to say this constant is equal to b over a. So I can do that because I can just choose an appropriate b so that when divided by a, it's what we need. Okay, so now let's maybe clear denominators, or not clear denominators, but maybe to get rid of this fraction over here on the left-hand side. And that'll give us the arctan of x by a is equal to, so it's going to be ax plus b all over 2. And you might say, well, we could do a little bit more absorption here to get rid of that 2. I'm not sure that's super advantageous here because we have to keep in mind that the scaling of this x minus a would also, or x over a would also be affected. Okay, so now let's take the tangent of both sides. Oh, and this should have been the arctan of z over a. So the tangent of both sides will give us z over a is equal to, let's see, tan of ax plus b all over 2, which means that z, which is equal to y prime, is equal to a times the tangent of ax plus b all over 2. But now we can take the antiderivative of both sides of this, keeping in mind that the antiderivative of tangent is, well, it's natural log of secant. And then this coefficient of x here is a over 2. Here we have a coefficient of a. So we almost have enough to not worry about what's up front, but I think we need to multiply in a 2. So we have natural, or 2 times the natural log of the secant of ax plus b all over 2. And then we'll have plus a constant of integration. So there's our solution in this case. And I guess I should say that technically perhaps we should have absolute value in here, but I'm kind of playing it fast and loose with that. Let's just say that we're working on an interval where the secant is positive. Okay, so anyway, let's move on to the last case, which is when a is positive and we have a minus sign here. So now we're finishing it off with our last case, which is when we have a is positive and we have a minus sign here. So let's just jump right away to our variables being separated. And we'll have dy over y squared minus a squared is equal to 1/2 dx. Then we can take the antiderivative of both sides, and then we'll need to do a partial fraction decomposition over here on the left. It's a fairly straightforward though one, so I'll just write it as 1 over 2a, and then we have the antiderivative of 1 over z minus a. Oh, this should have been a z. We're still in the z variable. And then minus 1 over z plus a. And then this is our dz. Okay, great. And then we'll have a 1/2 dx on the other side. So here we have 1/2 antiderivative dx. And then let's observe immediately that we have these two floating 2's in the denominator that we can cancel. Okay, great. And now let's take some antiderivatives. So taking the antiderivative of the left-hand side will give us 1 over a. And then we have natural log of z minus a minus natural log of z plus a. Great. And then that's going to be equal to x plus b. So that's our new constant. Okay, but now here we have 1 over a, or maybe I'll go ahead and multiply the a through. And while I'm at it, let's start off by taking this constant to be b over a so it simplifies nicely. So I'll have natural log of z minus a over z plus a. There I'm using logarithm rules equals ax plus b. Okay, nice. But now let's exponentiate both sides. So that'll give us z minus a over z plus a equals e to the ax plus b. But then we can separate that out into e to the ax times e to the b. But then we can just rename that e to the b, maybe a new value of b. So here we could just set this equal to b. And I guess we could do that by saying that this b right here is really natural log of b, and this b right here is really natural log of b as well. But I think it's like kind of useful just to get used to renaming these constants on the fly. So I guess I should say here, we replaced b with e to the b, or maybe we replaced e to the b with b, depending on which direction you're thinking about it. But now from here, we can solve for z pretty easily, and we'll end up with z is equal to, let's see, it'll be a plus ab times e to the ax over 1 minus b times e to the ax. So the idea here is you just cross multiply that z to the a or z plus a up, and then you collect all the z's on one side of the equation, everything without z's on the other side of the equation, and then you get this right here. But now I'm going to actually separate this out into two pieces, and that is a over 1 minus b times e to the ax plus a times b times e to the ax over 1 minus b times e to the ax. And that's actually going to be the form that I'll need it in to solve our final differential equation, which is y prime equals z. So here, let's write that up here. So now we have y prime is equal to, well, it's this first term, which I'm actually going to do one more thing to, and that is multiply the numerator and the denominator by e to the minus ax. So that'll give me a e to the minus ax over e to the minus ax minus b, and then we'll have plus ab times e to the ax over 1 minus b times e to the ax. Okay, so now that we have it in that form, we're ready to finish this off. So we're in our last couple of steps. And here we've got y prime is equal to, well, that function involving a bunch of e to the a or minus a times x. So now I'm going to rewrite this by taking the integral as y equals the integral of a times e to the minus ax over e to the minus ax minus b. And sorry, that should have been a plus b dx plus the integral of the next one. So that'll be ab e to the ax over 1 minus b e to the ax dx. And now I'm going to perform a substitution on each of these, and it'll be a different substitution. So for this first one, I'll set maybe t equal to e to the minus ax. So that's going to make dt equal minus a times e to the minus ax dx. And then for this second one, I'm going to set, I'll maybe use s equal to e to the ax. That makes ds equal to a e to the ax dx. Okay, great. So now I can change this out to y equals, well, I'm going to pick up a minus sign from this minus sign, and then I'll have the antiderivative of dt over, let's see, it'll be t plus b. Then let's see, I don't pick up a minus sign over there, but now I'll have the antiderivative of b times ds over 1 minus b times s ds. So that's kind of funny that we have b times s in the denominator there. Okay, great. But now we can take antiderivatives, and we'll have, let's see, minus natural log of t plus b, but recall that t is this. So we have e to the minus ax plus b. And then here we're going to pick up a minus sign from this antiderivative, and then this b will cancel. So we'll have minus the natural log of 1 minus b times s, but now s is this e to the ax. So it's 1 minus e to the ax, and then plus our new constant c. But now we can push both of these together, and we'll finally get the natural log of 1 over their product. You know, we're using those minus signs to put them in the denominator. So we'll have e to the minus ax plus b over 1 minus b times e to the ax, where I just realized I forgot a b right there. Okay, and then we'll have our new plus some constant. And then I believe maybe there's one more simplifying step we can do. We can multiply the numerator and the denominator by e to the ax. So that gives us the natural log of e to the ax all over. Now we'll have b e to the ax plus 1 times 1 minus b e to the ax. But that turns into a difference of squares. So it'll be 1 minus b squared e to the 2ax. Okay, and there we have it. We'll make sure we have our plus a constant. I think that's a really nice form of our final solution, and that's a good place to stop.